During this talk, I'm going to refer to a diagram I drew that shows us the entire environment. And this gives us a way to picture where performance tools are applied and how methodologies walk through the different components involved. And so this is just a generic diagram that shows the operating system and then hardware components. My name is Brendan. I'm a lead performance engineer at Joyent. My work and research is on performance tools, visualizations, and methodologies. Some people know me from my work at Sun or Oracle, and I'm now at Joyent. Just very briefly, Joyent is a high-performance cloud infrastructure company. We compete on cloud instance performance, and so as part of my day job, I get to make sure that our instances are performing the best. So using these tools is what I do all the time. We have KVM for Linux guests. Last year I gave a talk at Scale on cloud performance analysis, and that talk was about operating systems in a very generic manner. I didn't talk about any in particular. This year I'm talking about Linux performance analysis, and I'm very, very happy to be back at Scale, so thank you. And this is also the primary operating system for my next book, which is Systems Performance by Prentice Hall. In secondary, I'm doing the OpenSolaris or Lumos-based SmartOS. I'm using Linux as the primary operating system for examples. In this talk, I'm going to do a very brief rundown on performance. A lot of this should be obvious. Then a Linux analysis and tools, and I've broken that into basic, intermediate, and advanced groups. And then the methodologies for applying them, so that you can see how they work and how to follow them on the system. So to start with performance, why are we doing it? Performance, this may be pretty obvious, so just background. Performance helps you reduce IT spend. And for many of us in cloud computing environments, by making my instances perform well, it means I can realize an immediate cost savings by running fewer instances. So finding and eliminating waste, finding areas to tune and doing more with less. Building scalable architectures, also as is the case in cloud computing, you all want your applications to scale well and efficiently. And so studying performance helps you understand the limits that you're encountering so that you can develop around them. Also solving issues, and that's kind of what I do most of the time, is finding performance bottlenecks and issues and solving them. Why study the operating system? There is a saying in performance where performance is best tuned closest to where the work is performed, and the work is performed in the application, so performance is best tuned in the application. And there are many companies that spend so much effort in this and have really great performance wins by studying the application that the operating system kind of gets overlooked. They don't actually dig down very often at that level. So studying the operating system is definitely worthwhile. There are two reasons for that. One is finding and fixing kernel-based performance issues, and that includes the sort of 2 to 20% wins with tuning higher buffer sizes, making sure the NUMA is working correctly for memory locality and so on. The sort of small kernel tunables that are worthwhile to have, although they're not huge wins. There are, in the operating system and in the kernel, there are sometimes very big wins, 2 to 200x, where there are latency outliers and you're finding ways to eliminate them. And so my application has these 1 second latencies to the kernel, maybe scheduling, and I've found a way to fix that. Kernels change, new devices are added, workload scale, new performance issues are encountered. So even though the operating system sounds like it's been around for a long time, from a Unix-based operating system from the 70s and Linux from the 90s, there are always new devices and new workloads we're throwing at them. So there's always plenty of work to do in the actual operating system and in the kernel. The other activity for studying the operating system is that sometimes it is the best way to find those application level issues. So by using the operating system toolset, I can tune the application and see the application is making the devices do this. And that's where I'm tuning the application, I'm eliminating unnecessary work, and that's where you can get the really big wins. Another way to clear up a little bit of confusion with performance, with system analysis, it can be top-down and bottom-up, and that depends on your perspective. and sometimes people argue about which way is right, but these are two valid ways for approaching performance. Developers are looking at their workload and how that's applied, and will typically start at the application level and drill down, where sysadmins start at the device level and move up, the devices that they're responsible for, and look at tools that are centric for them. If you're doing performance as a day job like I do, I use both approaches. They're both valid, and they're both useful for finding issues. Eventually, you'll need to know some kernel internals, and we'll see some of that during this talk. Another thing that's worthwhile picking up is system metrics, and there's just a very simple output from IOSTAT. It's worth studying system metrics, and I have many text examples in this talk, even if you never intend to use the text-based tools. So if you're using performance monitoring GUIs, a lot of them are based on /proc, they're based on SAR, they're based on the VM stats and IOSTATs. And once you really understand what the metrics do once, then when you go and use the other tools, it's the same thing. So even though I'll be using some CLI examples, your goal may be to use some performance monitoring software, and that's fine. You'll find that the metrics are often the same. So it's a very quick background of what we're going to do in performance. Analysis and tools. So I'd like to do a quick tour of tools that exist and show what can be done. And part of this is letting you realize that finding any sort of unknown that you weren't thinking to check, so that you can see that they can be analyzed, and then some methodologies for applying these. So back to our picture, operating system and hardware. The tools that I'll go through include these. And this is kind of what's in my mind, even though this is still a generic picture of where the tools are applied. And of course, I'm paying attention not just to the components, but also to the interconnects of the components to find out where find out exactly where performance bottlenecks may be. Performance bottlenecks can be anywhere. So you kind of, especially for the really serious issues, you don't want to leave any stone unturned. Basic tools. I'll go through this quickly. This might be pretty obvious. Some of this you probably use almost every day. Uptime has the load averages. These are shown by other tools. They're often described as the 1, 5, and 15-minute load averages, and they're often described as being CPU-based. These, on Linux, these are now including the tasks that are blocked on disk I/O as well as CPU usage. And they aren't exactly 1, 5, and 15-minute averages. The calculation is an exponentially damped moving average. 1, 5, and 15 minutes are constants that are used as part of the equation. And so they're showing recent usage. The three values are provided so that you can get a sense of, are things getting worse, or are things getting better, or are things getting steady? If you study load averages, over time you may encounter documentation that suggests if the load is greater than the CPU count, then the CPUs are saturated because I have more tasks or threads that are runnable than CPUs to service them. That doesn't quite work on Linux with the disk I/O factor as well. So your load average can go up because of disk I/O, and that's included as part of load. But I wouldn't stress too much about load averages. These are a clue to understanding system health, and I spend 10 seconds looking at them, getting an idea if load is getting worse or better, and then move on to other tools. Tools like TOP, which you may use every day to solve issues, and solve real issues. TOP's been around for a long time. Bill Lefebvre wrote it, and inspired a little bit by a VMS command. And it has, I'm sure a lot of this is obvious, it has the system-wide summary at the top and per process summaries, which show us virtual memory resident set size, the memory usage, shared memory state, percent CPU, percent memory, CPU time consumed. So it's a very quick way to find out what processors are consuming the CPUs. And the percent CPU sum it's giving us on Linux is the interval sum, the sum between intervals or screen refreshes. This does vary on other operating systems that normalize it or average it across the CPUs. So again, you might hit some documentation that sounds confusing. Top can consume CPU cycles. The syscalls it's using to read proc over and over for each stream update. You might encounter a version that reduces that by using pread, so it's not doing open, read, close all the time. Seems straightforward, and it's in the basic set of tools. Maybe a couple of interview questions would be, does it show all CPU consumers? If I'm running top because I have a CPU issue, is that list everything? Is there anything missing off that list? A second interview question, a process has high CPU percent, what's the next steps for analysis? So you might think about how you might answer these. It's a fun to exercise. So top can miss short-lived processes, so processes that come and go between screen updates. It may not be listing kernel tasks unless you've included it, and there are many versions of top that provide options for that. In the process listing, you may have some CPU consumers, I can put there, you may have some CPU consumers that are not process-based, so you may have some hardware interrupts that are consuming CPU cycles, though you can sort of figure that out in the top summary. Analyzing high CPU processes. So I have a process that is consuming a lot of CPU, and I can identify why by profiling the code path, and I can identify what the CPU, percent CPU actually means by studying the executional stall cycles. So maybe I should have come up with an interview question for that. What does percent CPU actually mean? So it means a task went on CPU, it did stuff, and then it left, and the kernel scheduler took it off. During the, and it bumps bean counts when it does that. During the time it's on CPU, you might get the impression that it's doing execution cycles. The processor is doing work, it's doing the fetch, decode, and operating on instructions all the time, whereas this includes memory stall cycles. And CPUs are getting faster and faster, and memory's not getting as fast. And often I'm seeing performance issues, especially when I'm helping design architecture, where it's actually the memory bus is becoming slow, and that's presented to you as percent CPU. So yes, I have high percent CPU. It's because NUMA isn't configured properly, or the memory I/O is slower, and I've got a lot of stall cycles. And that just makes all of those CPU operations take longer. I'll talk about how to analyze that a bit later. Just going through the basic tools. HTOP is great, super top, super configurable. Has a basic CPU visualization at the top, where you can see if there are hot CPUs and how the workload is balanced, if you configure it that way. I configured it that way. The traditional tool for this is MPStat, for multiprocessor statistics. And these columns are summarized at the top of the top's header. I'm generally looking at the last column, idle, to see how much headroom I have and to figure out the workload balance. But there's other neat things you can learn from that. IOStat is another basic tool, and I actually really like IOStat. I am a bit of a performance tool geek, and this one I think is actually well designed. It's been this way since AT&T when it originated. You have the workload input columns that show the workload that's applied to the disk. It's actually the block device interface. And then you have the resulting performance for the remaining columns. I had to kind of draw it twice in the slide because it's more than 80 characters. So one of the reasons I like my tools to stick within 80 characters is because it makes it easier to do slides as well as putting them in books. So think about that if you're designing tools. But aside from that, the columns are fantastic because there are times when the performance issues can just be about the input that's applied. And so those are the columns there, and then the resulting performance, which includes things like the average queue length, average wait, so I can see the latency. I didn't highlight service time because it's inferred, and it can be a bit confusing for virtual devices. And percent util, which shows how long it was busy. Percent util, the usefulness depends on the target. Virtual devices backed by multiple disks can accept more work at 100% utilization, which might be confusing. You can also use the IOStat output. It's showing me per device, but I can use the output to figure out I/O controller statistics, which is part of my map of the system, by summing related devices. It's one little nit. I'd like IOStat to have -E so I can see errors, device errors. VMstat is another basic tool, just to go through it quickly. Virtual memory statistics, been around for a long time, since BSD. First line of output on Linux has some summary since boot values, which is a bit confusing. R is the total number of runnable threads, including those running. That does differ on other OSs. Swapping, which is kind of why I'm using this, which is traditionally known as paging, allows oversubscription of main memory by swapping pages to disk if you have a swap file or a swap device configured that costs performance. You generally don't want your systems to be swapping because as the application is running, when it thinks it's talking to memory, now it's talking to disk, and that's a performance cliff. So if I'm doing swapping, then some applications generally being bad and has grown to consume system memory. Another very basic tool is the free command to find out how much free memory there is and the size of the buffer cache for block device I/O and the page cache for file systems. Another basic tool, ping, very straightforward. I have an example here that shows pretty stunning ping times. This is actually collected from the hotel room at this hotel. So I think we're all a bit familiar with that sort of. Usually ping is not that interesting actually because the latency is very small, but this output was actually pretty interesting. And that was me picking a good one. It tells us some, but not a lot. So it's actually kernel to kernel IP stack latency, including how the network handles ICMP. And the network may handle ICMP differently to TCP and other packets. So try to use TCP options. There's HPing and there's other tools out there for analysis. It is kind of useful. It is useful to have a simple tool, even though it doesn't test much. That lets me test one thing and then move on. A tool I wanted out of frustration that I finally wrote for a different operating system a long time ago. Tim Cook did the port to Linux. This is called NICStat, and NICStat, I kind of designed it based on IOStat because I love IOStat, but I want the workload input and then the resulting performance per device. And so the workload input has the read kilobytes, write kilobytes, packet rates, and average size, then the resulting performance in terms of device utilization, the max per direction, and then saturation, the saturation statistic. So you can find out if a network device is pushed to its limit, how much oversaturated is it? Like with IOStat, you can actually use this if you needed to calculate network controller statistics by summing throughput per port, per controller, by summing up the related interfaces. There's another tool which is in a similar vein, DStat, coming up with, instead of continuing to use old tools, but trying to rethink it and trying to come up with easier ones that are more useful. DStat, a better VMstat-like tool, and let's read on the columns. It's a nice summary. It does coloring for what it's worth. I'm not a huge fan of coloring when it comes to subjective performance metrics because people have different opinions about how to apply them, but it certainly does, can be easier to read. And DStat has lots of, you can do plugins for DStat and extend it. So that was a basic tool set, very, very quickly. And this may represent some of the tools that you use often. That's the observability, the basic observability you have based on them. So there are a lot of gaps. I've got some arrows here for what you inferred. And so like I said, with IOStat and NICStat, if you add the devices, you can kind of infer controller throughput and packet rates and what have you. But there's still a lot of stuff we have gaps. Intermediate tools. Again, very quickly, and then I get to do advanced. SAR, NetStat, PIDStat, and so on. SAR is a system activity reporter. It has kind of a bad reputation on other operating systems because it's been buggy, but it's actually pretty good on Linux. It has lots of really useful options. You can configure it to archive statistics from cron. And the example I've got here, it's too small, but I'll post the slides on SlideShare. It's got I'm doing paging statistics -B. So you can see the pages paged in, pages paged out, page scans by kswapd, and page scans direct. So you can find out if I'm using swap, then am I doing swapping? many statistics available. And of course, if you study these and learn these, if you're using performance monitoring tools, a lot of them are based on the SAS statistics anyway. There's NetStat for various network protocol statistics. The output varies based on the Linux kernel version, especially TCP extended statistics. And you have things like active connection openings, passive connection openings, failed connection attempts, and so on. Active and passive are, of course, the original TCP terminology for what's commonly called outbound and inbound connections, or connect or accept if you want to use the socket terminology. And this also has segments. We've got segments send out and segments retransmitted. And so as a very basic test of network health, you might try and calculate the retransmission rate. And it also depends on who the clients are. So if my clients at the server are mobile phones and very unreliable devices, I will have higher retransmissions. But there's lots of extended numbers when you're investigating weird network issues that you can pick through. PIDStat has very useful process breakdowns. It doesn't clear the screen by default, which is my preference. So every time I'm using one of the top tools, I'm like, where's the switch that doesn't clear the screen? Because I want to see it roll up so that I can compare history from second to second. So anyway, your preferences vary, and that's fine. Very useful process breakdowns. And so PIDStat 1, I can see user and system for each process. PIDStat -D, if you have the kernel stuff enabled, you can see disk I/O. Now, it's doing it in terms of kilobytes, which is very rough and difficult to interpret because you don't know if those kilobytes are random I/O or sequential I/O. So kilobytes can differ, but at least it gives you something. And sometimes when the disks are rattling and you're like, I don't think it's my application, I think there's some other thing that's rattling my disks. Who is it? This may be a very quick way to identify that. So PIDStat -D is one of my favorite tools. strace for the system call tracer. And some of you may have seen a talk on strace yesterday, which I hope was really good. I'm sorry I missed it. strace can be used for performance analysis. I've got an example here that does strace minus TTT for the microsecond timestamp since epoch, and then minus capT for the time spent in the system call. And I can attach it to processes or run a command. One of the difficulties with strace is you have to attach it to something, so you can't just strace the entire system. It is really useful because high application latency is often caused by resource I/O, and most resource I/O is performed by system calls. So like disk I/O, you're actually going via a system call for that. Is there any I/O that's not performed by system calls? So memory mapped I/O may not be. Yeah, memory mapped I/O. So yeah, exactly. So just to bear in mind that while we can investigate some I/O issues, it's not 100%. You might have something configured that's doing memory mapped, and it's actually doing page faults to do I/O by doing direct memory access. -C to print a summary, and I had an example that did a DD from dev0 to dev null. I did this on purpose to demonstrate the worst case strace overhead. And so while strace is actually a really nice tool and does translation of the syscalls that they're running, and you can learn a lot about applications and performance, you do have to know that it does cost. And it's interrupting the processes it's tracing it, which it behaves in a very violent manner as it's inspecting the target. And as a demonstration of worst case overhead, it's not going to be this bad, but worst case overhead, I ran strace on DD and it ran 200 times slower. Because DD was pretty tight doing the system calls. Went from 1.5 gigabytes a second to 7.5 megabytes a second. So super cool. I do hesitate when I go to use it. Sometimes when your application is on fire and it couldn't actually get any worse, then it may not matter. So you can use strace to get yourself out of hell. But other times, I do hesitate. Something similar, but for network, instead of syscalls, for network I/O, there's TCP dump. Sniffing output packets, dump it to a file for post-analysis. Output has timestamps with microsecond resolution. That's great. You can study odd network latency packet by packet, and you can import this into other tools for analysis, like Wireshark. And especially for strace, if you've got a weird issue of I/O latency that can be useful, this is a weird issue of network I/O latency, and I can capture the dump file. It does have overhead in terms of CPU and storage. The previous example I had here did some packet drops, had 508 packet drops, and this was only a 1 gigabit Ethernet network. 10 gigabit Ethernet drives this much harder. Your TCP dump version should be using socket ring buffers to reduce the overhead, so it's not transferring it packet by packet to user land. I have heard of other ways you can use kernel modules to reduce overhead even further. I haven't used that myself. You can use filter expressions that get compiled and put into the kernel so that they can also help reduce overhead. It still ultimately can be problematic for busy interfaces. So it's another one of those tools. I use it because it can solve problems, but I hesitate to use it because of the overhead. It's something I need to think about and consider. It could be problematic for busy interfaces like 10 gigabit Ethernet. That was for networking. For the disk I/O level, there's different tools. Blocktrace is one of them, and Blocktrace has a convenience function called btrace, which runs blocktrace and blockpass. That's showing one single disk I/O event and all of the steps that happens in the I/O scheduler in Linux to process that and dispatch it. Really cool. And I have I've got high resolution timestamps in there. And just like with network packets, if you had some sort of weird suspected network latency, you do a TCP dump and then pick through it. With Blocktrace, you can do a disk dump and then pick through it. And I've seen people put this into visualization tools as well to try and figure out how the disks are being used. Great for investigating I/O latency outliers. IOTop is another one for disk I/O. And IOTop shows us disk I/O by process if you've got the things turned on in the kernel. And the I/O column is the time the thread was waiting on I/O. This is even more useful than kilobytes. I said kilobytes, well, you don't know if it's random or sequential, and so it's not a universal currency, whereas time is the universal currency. I can compare that, and so I've got the time that the application was prevented running because it was waiting on the disks. So here I've got a checksum command that was spent 80% waiting. So I do like IOTop. I may have written the first version a long time ago prior to that. SlabTop for investigating kernel slab allocator usage. And great if you're trying to understand the kernel seems to have consumed more memory than I'd expect. Where exactly is it? And so the slab allocator is really efficient, high-performing memory allocator. And one of the convenient things about, as a performance guy, one of the convenient things about the way the slab allocator works is you have to create these slab caches. And for me, the kernel engineer is unwittingly documenting kernel memory so that I've got statistics that I can then use to debug and analyze. So can you imagine like looking at a process heap that has nothing? So the kernel's not like that anymore. It's not like the buddy allocator, but we've got the slab allocator. So we have some really good metrics of the reason why memory is used. I threw CTL in here just for the intermediate commands, and that's part of static performance tuning. Static performance tuning is a methodology where you're not looking at the input to the system and you're not looking at the resulting performance. You're actually looking at the configured system, how the system is configured, even without a workload applied. So even when the workload is shut down, maybe it's been misconfigured, maybe options have been overlooked, maybe the server has been repurposed, and someone forgot to change the TCP parameters for the new reason. Static performance tuning was popularized by Richard Elling, who's sitting in the audience. He's giving a talk later. He wrote a paper many, many years ago about this. So, but it's great to actually put a name on the methodology. So I remember to check the configuration of the system, even though there's no workload applied, because something can be overlooked. And proc, I added that to the intermediate tools because I can read many useful statistics sources directly. And there's also proc VMstat, which has lots of cool stuff. There's my intermediate recap. Now I can get into the advanced, so basic and intermediate, much of that may have just been recapped for you. Some advanced tools, Perf, dtrace, system tab, and more. So Perf, this was originally performance counters for Linux. It focused on CPU performance counters. These are the programmable registers, so I can find out what the CPUs are doing and what the buses are doing. And Perf has evolved, so it's now a collection of profiling and tracing tools with numerous subcommands. And it's actually really cool. I really like Perf. Anyone actually a like-minded fan of Perf? Hands up if you've used Perf. Okay, so I've got maybe 5%, 10% of people. So Perf's cool. Some of the subcommands include kmem for tracing memory, kernel memory slab properties, kvm if you've got kvm guests. So you can look at the exit events and find out why their performance might be bad. Listing the available events, and there's lots that you can instrument. Analyzing lock events, creating dynamic probe points. Yes, dynamic tracing is in here as well. And there's scheduler statistics, and there's stat. Stat is the original purpose of Perf. This operates on the CPU performance counters. So these are hardware. These are a hardware resource that you can program to measure events. They're kind of weird because most counters you use in the operating system are software kernel counters, and there are a lot of things you take for granted, like people can read all the different counters at the same time. Since CPU performance counters are a fixed hardware resource, there may be between 2 and 12 per CPU. If one person is using them to measure something, other people can't use them at the same time. Performance is busy. Or the Perf has to do a multiplexing so that I can look at one process and you can look at a different process. They'll actually shuffle around the registers as they context switch. So okay, there's a few challenges actually to use performance counters, but they're really worth it. I've highlighted something here, I run perfstat gzip file 1, and I've highlighted IPC. I tend to think about it the other way around, cycles per instruction, but that's instructions per cycle. And this makes it so easy to get, just running perfstat. This is actually, if you're familiar with other operating systems, try to do this because it's actually really hard. And Linux Perf makes it really, really, really easy. The top example I gave earlier, and I said the percent CPU, and we weren't sure if it was memory stall cycles or CPU instructions. That is the next thing you look at is IPC. Because IPC, if IPC is actually very low, if it's less than 0.2, it means we have fewer instructions per cycle. And it likely means that we're stalled on memory I/O. It could be stalled on other device I/O as well, which you can investigate. And once you know that, once you look at IPC and you figure that out, you know that even though the system has run out of CPU, faster CPUs is not going to help. Faster CPUs means they're just going to stall quicker. It's still waiting on memory I/O. And so this is a very important determining factor. I can get much more information out of Perf. So I can choose different counters, and again, Perf makes it painfully easy. Perf stat -c instruction cycles, level 1 data cache load misses, last level cache load misses, data TLB load misses, and it's printed them out right there. It also supports additional custom counters. You can provide them in hexadecimal, and there's a new description syntax for that, for whatever the processor supports. And why you do this is because you want to understand this sort of stuff. I want to understand exactly what the CPU interconnect is doing, what the CPU is doing, the floating point operations, CPU cycles, it's hardware CPU caches, which there's more inside a CPU than you probably think. You need to read the processor manual. What the memory bus is doing, what the I/O bus is doing, whether it's quick path interconnect or AMD's hypertransport. And you may be able to go even further off the CPU and figure some things out as well. If you are going to do this, you spend quality time with the vendor processor manuals, like the BIOS developer, kernel developer user guide, and they're really thick and really long. But generally, if you sit down, it's like, I need to understand this bus. It's probably a day's work to go through the manual and figure it out. It is fantastic that it's doable. And so it's a sort of case where I may not do this every day, but when there's a really important issue, or I'm designing hardware, I'm designing a product, it's worth the expense, it's worth the investment. And of course, I hope we actually add tools to make this sort of thing easier. That's only one thing Perf does. Perf does a lot of things. I could give a whole talk on Perf, although I'm trying to just give it one section. Perf profiles CPU activity as well. So Perf record all CPUs, cold stacks. This is my arbitrary frequency. And then sleep10 is just a dummy command. Generates a perf.data file, which I can then analyze using Perf report. I can also use Perf to profile other events, like hardware events. So I can say, generate the perf.data file based on CPU cache misses or memory I/O or things like that. Here I'm reading perf.data. I'm focusing on the non-interactive mode using --STT_IO. And this goes as far as you probably can with a text interface for summarizing what's actually a massive file full of data. So it's coalescing the common stacks so you can quickly identify why the CPUs were used. Perf, if I don't use --STT_IO, it has an ncurses interactive wizard so that I can dig through the perf.data file that way. Since this is a very common thing, by profiling CPUs, so with perf state you can kind of figure out whether it's memory stall cycles or not. By profiling the CPUs, you figure out who is using the CPUs. So what code paths are making the CPUs busy. It's such a frequent activity, and I do this not just in Perf, but in many, many other tools as well, the exact same stuff, just profiling call stacks, that I came up with a visualization called flame graphs, and I've written it so that it accepts the Perf files as well. It's an interactive SVG, which I couldn't demonstrate in the slide, but I think I loaded it. It's an interactive SVG, it's probably too small to see, but I can move the mouse around, and at the bottom, it's showing the percent of samples that were included that function. And so this particular one is I've got the Linux kernel and I was investigating a particular issue, and I can quickly identify that I'm spending 87% of my time in IP output on CPU. And being able to quantify it and then quantify why very quickly, just by moving the mouse around, as a performance engineer, this is hugely valuable, as I can quickly exonerate areas of the system and then blame other areas of the system by saying, yes, I quantified it, it is this area that needs to be tuned. So the slide doesn't do it justice because it is interactive, but just a very, very simple description of what this is. On the y-axis is the call stack, that's the stack frames. On the x-axis is not the passage of time. This is the population of samples. And so that doing the passage of time is actually almost too expensive to do in terms of performance overhead. So this is a simplifying factor that actually made it very practical. And so I use this all the time. Other communities like Node.js are starting to use flame graphs a lot for solving issues. And it's just whatever profile data, it's just a way to visualize. It's actually a Perl program I stuck on GitHub, it's like 100 lines. It's a very small thing that just spits out a speed. Static tracing. Perf does static tracing as well, and this is where the kernel has trace points that programs or engineers have designed to put in deliberate locations so that we can understand what's going on. I've said perf less pipe grep block, and it's shown the block I/O trace points. There's 840 for this particular kernel version. This kind of shows where the trace points are instrumented. So I've got socket I/O, syscalls, ext4 block. That's pretty cool. More can be added as needed. These are, in some ways, these are useful breadcrumbs, because if you're unfamiliar with the kernel and you try to read the source code, it's pretty verbose. But if you look at where instrumentation has been placed, this is where an engineer has said, yes, this thing is interesting, and this thing is interesting. So it actually helps as a form of documentation for me to work my way through the kernel and find out interesting places. More can be added as needed. I will use them. Dynamic tracing. That's static tracing, where the engineer has to put a trace point into the code to use. And dynamic tracing is different, where you can create trace points on the fly based on the kernel source code. And so I've got an example here where I've said perf probe --add TCP send message. This is just a very basic example. Then perf record, and then reporting it. I did a -G for call stacks, and now I can see when TCP send message was called, this is the stack backtrace. This is dynamic tracing. This is dynamic tracing in perf. Has anyone used dynamic tracing in perf? Hands up. There is no one. So maybe because you didn't know it was there, that's fine. It allows you to put your finger on any kernel location and say, I want to know how I got there, and start tracing it. If you're thinking, but Brendan, you just showed this to me. You just showed me these like call stacks and flame graphs. It is different because this is sampling the CPU at fixed intervals, like 997 Hertz. What's cool about tracing, dynamic tracing, is that I may be hunting down IO latency outliers that are very infrequent, and they're just going to miss the samples. I can include other stuff in the perf data file. This is just a very basic example where I've said TCP send message. I can add like local variables as well. It's actually very cool. That gives you an idea of where dynamic tracing has the potential for instrumentation. I've only used perf for up to this syscall interface, the kernel. But once it works with uprobes, you can investigate more. It's an advanced activity. You don't have to refer to the kernel source code because it's exposing that, unlike the static trace points which have been documented for you. It fills in observability gaps. It has awesome capability. It does take some effort to use. You're waiting for the trace stub analyze cycle, and then using post processes to rework the output, or there is actually a perf scripting capability I didn't demo that you can use as well. Now, it would be the awesomest tool ever. I do like perf. It's actually does a lot of things very, very well. Would be the awesomest tool ever if it wasn't for dtrace. And now I have this has become the unofficial mascot of dtrace. It's the dtrace ponycorn X-raying a total, which I guess represents slow software. Dtrace is programmable real-time, unlike perfFence, where it's not quite programmable, it's not quite real-time. Does dynamic and static tracing. It's for performance analysis and troubleshooting without restarting anything. It's used on a lot of operating systems, so Flash, SmartOS, macOS X, FreeBSD. And there are 2 ports in development for Linux that we know of. One of them is dtrace for Linux, mostly by one guy in the UK, Paul Fox, who has done a pretty reasonable job so far of making solid progress supporting it. And I've used that a lot to solve customer problems. There's also Oracle Enterprise Linux dtrace, and they've made, and I've studied that as well, they've made steady progress at their port. They seem to be heading in the right direction. It's going to take them a while, but it's great that we now have 2 ports of dtrace. Does anyone in the room actually use Oracle Enterprise Linux? How many Oracle Enterprise Linux users do we have? Now the heads are really turning. We have none. So
That's all right.
we have one. Great. So
I don't want to admit it.
So no, it should be important that Oracle are doing this, because once dtrace has been fully ported, that might give you a reason to use it. So this is great. It's winning you over by giving you technology you want. So it's great. It's great there's 2 different ports. I generally use dtrace for Linux on Ubuntu and Fedora and CentOS. The examples I'll go through quickly, just to give you an idea of it, are from the dtrace for Linux version. And it has like a function you can run to help set it up, make all, install, make load. So there I've run it, 281,000 probes. This is still a prototype, mostly written by one guy, and it can panic and freeze kernels. So it needs to be warned up front. So when I said I've been solving customer issues with it, since this can panic and freeze kernels, I can't run this in production, even though I would dearly love to. What I need to do is replicate the customer issue in the lab and then solve it there. Programming capabilities allow for powerful, efficient one-liners and scripts. So for example, here's TCP send message again, but I'm saying filter on SSHD and quantize the size of the TCP send message. And so I can see the size of TCP send message packet straight away. It's a nice distribution. It's done. This is a filter that gets applied in the kernel, so we're reducing overhead there. It has an aggregation summary. And what actually happens, and this is part of dtrace has been designed for low overhead. As part of that, it only transfers from kernel to user land the right-hand column of numbers, along with the power of 2 designators, once a second by default. And so it's already done the summary in the kernel, where it's traced it, and then we get the information we want out. You can build GUIs upon it because it has such a low overhead. A particular example is from Joint Cloud Analytics, which shows the cloud-wide syscall latency. And again, this is like, I would hesitate to run strace on an entire cloud and just leave it running. But we can run dtrace on the entire cloud because it does the per CPU buffers, it does this asynchronous passage of data from kernel to user land. So it does not have similar overheads. Oh, and also I'm doing latency as a heat map, where passage of time is the x-axis and latency is the y-axis, because often latency is bimodal or trimodal when you have caches in play in different code paths, and I want to understand that. So I don't want to average it. I don't want average plus standard distribution or 99th percentile. I actually want the full distribution, because often it does have more than one mode. dtrace has advanced capabilities. It's not necessarily difficult. You may just use one-liners. You may use scripts. For example, the dtrace toolkit, dtrace book, which I'm the primary author of, has a lot of examples. Although they need to be ported, many of them need to be ported to Linux. And you may just Google them. You need to tweak one-liners, and you may tweak one-liners in scripts a little, so you may not actually learn how to program in dtrace fully. You may learn just enough for you to tweak things. Or you can ask someone else to write the scripts you need. Just by having the capability, the capability to solve all the problems you want, you don't have to write the scripts yourselves. I have a lot of sysadmins say, it's nice, but I'm not a kernel guy and I'm not going to be writing this. It's like, well, someone on your team can, or you can Google it, or... just a few more examples. I've got dtrace looking at the VFS interface. So VFS read, entry, and return. And I won't go through the syntax. There's a tutorial online. But for a 13-line script, this is demonstrated on Linux, I can look at VFS reads by process name, and I can see this is read latency distribution. And I can see 0.5 milliseconds to 33 millisecond disk I/O while tracing. The CLI syntax, just to put a slide in there, dtrace -n, provider, module function name, my optional filter, and then the action to perform. The provider is a library of related probes, and then module and function show whether the probe is located, and then I've got the name of the probe. And I've got the online reference there. I wanted to mention the provider because these are the providers that will ultimately be available. These are the ones that have been created for dtrace on other operating systems. So this is being ported to Linux. So basically everything, there's a whole heap of stuff for applications where we've got the JavaScript provider and Perl and Ruby and Objective-C and TCL and MySQL and so on. A couple more examples from Linux. These ones are using FBT, the kernel dynamic tracing. EXT, I haven't actually released, I've got this small collection of dtrace Linux scripts. I need to put them on GitHub, so this is the first time I'm showing them. ext4 slower.d. I want to see ext4 reads and writes slower than a specified latency with time, process, direction, size, and latency and file name. And that's what the script does. You run it, you give it an argument, and it only prints out the ext4io slower than that argument. I wrote this to answer, is ext4 to blame for latency outliers? So I may be looking for a 500 millisecond latency outlier. I can plug it into this script, and then it will only show me those that are slower. I put the source in the slide. It's traces, for this one I traced VFS and then dug it out of the kernel to the details I wanted, checked that it was ext4. And it's only 44 lines, and it immediately exonerates or blames ext4. So if you are, for a particular class of issues, if it's a single I/O latency outlier, and of course I can enhance this to include other classes of issues and other types, and I might step into ext4 and trace that directly as well. But this is a script that I like to use often, because when you have a customer thinking, my application has these weird latency outliers, is it the file system? Is there like some slow disk I/O? And sometimes there is. Sometimes disks can be really bad and misbehave. I can trace immediately the VFS interface and say, no, there are no disk I/O similar to the latency you're suffering. So we've exonerated the file system, please look somewhere else. Or maybe you do see it there, and you can then drill down. As another example, TCP retransmits, show me, TCP retransmits destination IP address, kernel stack to see why, and then in real time. I don't want to sniff all packets. I don't want to do the TCP dump post-analyze. I want to only trace retransmits to minimize overhead. There's the script, TCP retransmit.d. So this only traces retransmits, which are not in the HUD path, and so the overhead is minimized. And it tells me who it's retransmitting to, and gives me the kernel stack to say why. And it was like 11 lines of dtrace. Fortunately, because in Linux we have TCP retransmit SKB, a function that does the retransmit, which is fantastic. I can just dtrace that, and then dig out the other details I want. So yeah, another common activity I'm doing is chasing down retransmits, and this gives me the first pass at it, so that I don't have to sniff all packets. The current state of dtrace, this is demonstrated on a prototype dtrace for Linux. Right now it's not stable, and it needs other hand holding to work if you try it out. As far as I know, both ports of dtrace welcome help. That means you, so you can help either port reach success, reach completion. These examples were also FBT based, and so they'll need tweaks to match different kernel versions. That's why we have stable providers to solve that problem. But they're still being ported to Linux.
So FBT is FreeBSD?
Now FBT, it stands for function boundary tracing. What it means is it traces the entry to a kernel function and then the return from the kernel function, so the boundaries of the function. If you want to try out dtrace, I would recommend Lumos SmartOS. Lumos is the ongoing fork of the open source kernel, and SmartOS has joined the Lumos-based CloudOS distro. And we have dtrace and ZFS in there, and we use it for running Linux KVM on ZFS. But it has the mature implementation of dtrace if you just wanted to learn that.
Or do it on your MacBook.
What's that?
Or on Mac OS X.
Or on Mac OS X. So I'm on Mac OS X, and so I have dtrace installed here as well. And if you've got things like IOSnoop, so that's this is dtrace based. Whoa! So sudo IOSnoop, that's dtrace based. It's a script I wrote that Apple kindly ships on MacBooks, and you can see disk I/O live. So another way to try it out. Thanks. Other capabilities, there are many, which I won't go into, but I put a slide. SystemTap is the last tool I wanted to mention, and it was created when there weren't dtrace ports for Linux. It does a lot of the similar stuff. I have actually used it a lot, and I've run into problems with it, panicking and freezing and slow startups. So again, it's painful because dynamic tracing is fantastic, and I want to use this in production, but I can't because I hesitate because of the unreliability. So for a recap of the advanced tools, I've gone through tools that give you exposure to everything. There are more tools. This isn't all of them. Just going through the standard ones, basically to go through the main areas. But it can be confusing, so where do you start? And I've just got a very quick rundown on methodologies to end the talk. Methodologies. This is how you can figure out, given all these tools and all this capability, what on earth do I do with it? I've got 4. These give beginners a starting point, casual users a checklist, and experts a reminder. The first is the streetlight anti-method. This is included for comparison. This is this is an anti-methodology. This is not what we want you to use. Pick observability tools that are familiar, found on the internet or found at random, and then run them. Named after an observational bias called the streetlight effect, where a drunk is looking out under a streetlight, because that's where the light is best. And I kind of see it frequently because people are running top long after it made sense. Top is great, but they have an issue where top isn't going to solve it, but they're still running top because it's familiar. So it's a tools-based approach. It's inefficient, it can take time, it can be wasteful, and it's incomplete. So you may not find the right tool, and the right tool may not exist. You may need to develop it. But with streetlight effect, you're just looking at familiar tools and trying them out. A different methodology for applying tools is workload characterization, and that's where we focus on the input to the system. So who, why, what, and how is the load being applied, and characterizing those factors. This identifies issues of load, and the best performance wins are issues of load. This is eliminating unnecessary work. Don't fall into the trap of assuming you know what the load is. To characterize it, people say, I know what disk I/O is. I'm running a database, it's going to be the database. It's like, well, you don't know that. It could be some cron tab backup or some development project that was left behind. So it's very useful to characterize it and figure it out. Pros, it's potentially the largest wins. Cons, it's only a class of issues and it's time consuming. Drill down analysis is, you may already be familiar with this. This is where you drill down through layers of the system to find the root cause. And as an example on ext4, I might just walk down the kernel stack. And so for example, I could use dtrace, and here I've picked up ext4 read pages, and I'm pulling out the latency as a distribution. Again, I'm using dtrace for Linux. And I can dig out other information like the stack, why I got there, as part of drill down analysis. So drill down analysis, that's another methodology, and that's where I'm starting at the high level and I'm drilling down until I find the root cause. Pros, you will identify the root cause. Cons, it's time consuming, especially if you start drilling in the wrong direction. And the last methodology is the use method. This is one that I've come up with and was published in this month's CACM. For every resource, check utilization, saturation, and errors. And it might sound familiar to queuing theory, which is fine. It's, if that helps you apply it. So utilization is the device and how busy it is. Saturation is how much work is queued. And errors, of course, is what has errored. For the targets of the use method, find every item in the data path, especially if there's a functional diagram like the diagrams I've been using. And so everything on that, ask yourself, how do I check utilization, saturation, and errors for every component? I have got a performance checklist for Linux, which I put on my blog. It's very long, it would fill a dozen slides, where I go through the combinations. And there's a lot of unfinished work there that needs to be done as well. You can apply the use method for software resources, like mutex locks, thread pools, process and thread capacity, and so on. So from mutex, utilization, saturation, and errors, utilization can be the time it was held by everyone. Saturation can be how many tasks or threads are queued on it. And errors, of course, if it has errors as part of its interface. The use method can reveal missing metrics, because instead of starting with the tools, you're starting with what you want to see. I want to see everything in the data path, every component. And so they are your known unknowns, much better than unknown unknowns before you knew they existed. Tools can be developed to help the use method. And so there are many, many tops out there, but I'd like an interconnect top that showed me the utilization and saturation of the system interconnects and buses. So resource-based approach, it's a quick system health check. It isn't tied to the tools, it's tied to the questions. And it is efficient, because in some areas of the system, it's very uneven. You have dozens and dozens of TCP metrics, but then much fewer interrupt metrics. Whereas use method is picking the key 3 to check for each area. It's only limited to a class of issues, bottlenecks, and errors. So it doesn't solve anything, but it is a methodology in your toolbox. I did do a talk last year on other methodologies which you can look up. So there's many. So So the last slides I had, challenges for thinking ahead. Performance counter analysis, which I talked a little bit about, is actually pretty hard to do. I would like a perf bus top, not a bus stop, like or interconnect top, subcommand, that would be great. And the dtrace learning supports is still in progress. It'd be awesome when they're complete. In cloud computing, I didn't mention that, but for the functional diagram, you may not be hitting physical limits, you may be hitting limits imposed by the cloud provider, and so you need to check those as well. Hardware virtualization complicates things further because you can't see the physical components. And so hopefully the vendor will provide an API so you can see them, or you can ask the vendor to do that analysis for you. And we do that at Giant for cloud computing. So that's my talk. Thank you very much for attending. A very quick rundown of Linux performance analysis and tools and methodologies. I've got in the slides some references for further reading, and I will put these on SlideShare. If you follow me on Brendan Gregg on Twitter, I'll post the links so that you can find them quickly. And I think I'm out of time, but